Lab04 macroscopic view of DC and RC circuits. So our purpose is 1, predict the behavior of circuits containing resistors in series and parallel, and we use multimeters to measure the actual values of conventional current and potential differences in the circuits, and we examine the behavior of ohmic resistors and capacitors. So these are the physics principles we're going to apply. 1 is the node rule, which is the current entering a node in a circuit equal to the current leaving the node, and is due to the conservation of charge. And the loop rule, which is saying the change in potential for round trip is equal to 0. And then the change in potential equal to the current times the resistance. And these two are the parallel and series circuit resistance. So charge conservation and energy conservation in series circuit, part 1. So I predicted the current for I1 and I2 equal to 0.02 amps, and the actual current read by the amp meter is 0.02 as well. And the backwards amp meter would read negative 0.02 amps. So now we replaced one of the amp meters with a voltmeter, and then now the amp meter is reading 0 amps and voltmeter is reading 3 volts, and it's because due to the high resistance of voltmeter, the current is very small and is almost close to 0 on the resistor. So these are my potential differences from A to B to up to H, and then we can tell also using the loop rule, the change in potential for round trip is equal to 0. And this is the graph of potential versus position around the circuits. And we can see from E to F a steep slope, meaning there's a big change in potential, also meaning that large electric field. And that's the amp meter in parallel with 100 ohm resistor. And since the amp meter lowers the total resistance, this would cause the current to decrease as well. And these are my calculation for resistance for each component of the circuit. And now we're going to talk about the RC circuit. So first, with the battery, the bulb starts with bright light with uncharged capacitors. And sometime later, the capacitor starts being charged. So the light gets dimmer and current starts decreasing. And once the capacitor is fully charged, the light is out completely and current stops. So when we remove the battery and connect each wire, the capacitor starts fully charged, so the bulb is bright and current goes on. But once the capacitor starts being discharged this time, the light gets dimmer and current decreases. And once the capacitor is fully discharged, the light is out completely and the current stops completely as well. So these are my times to charge and discharge for each 10 ohm and 20 ohm bulbs, and approximately takes twice longer if the resistance of the bulb is twice as large. And this is my time-dependent voltage across a discharging capacitor for RC circuits. And the slope is -1 over the time constant resistance times capacitance, and it's approximately -0.16667. So we have 2 questions to answer. So 1 is, what if the lab was performed in real life and used an actual amp meter instead of an ideal? The real amp meter has resistance unlike the ideal one, so this would result in different values of potential difference in current. And what if the lab was performed in real life and used a real battery to charge a real capacitor without any resistor? Due to the presence of electric field and resistance of the battery, the capacitor will be charged much slower. Thank you.